So imagine you're walking down a winter street, right? And suddenly there's just this massive geyser of boiling water exploding out of the ground, cracking the asphalt, and completely flooding the intersection in freezing
Oh,
temperatures.
yeah. It's terrifying when that happens.
Right. And honestly, that catastrophic moment is like the only time we ever really think about the massive invisible circulatory system right beneath our feet. I mean, you and I, we just walk around looking up at glass skylines, completely ignoring the subterranean reality that makes the city habitable for you.
Exactly. I mean, it really takes a failure of that magnitude to remind us that we're entirely dependent on infrastructure we can't even see. Because cities are essentially just giant machines.
Yeah.
And heating is, well, the most demanding process those machines perform. We just take it for granted that when we turn a dial, the radiator gets warm. But behind that dial is a constant high-stakes battle of thermodynamics.
And urban economics too, right?
Oh, absolutely.
And that battle is the focus of today's deep dive. We are tackling this massive, everyday debate that's playing out globally. Basically, is it better to rely on a city's central heating, like those hidden underground veins? Or is it smarter to completely cut the cord, take matters into your own hands, and install an autonomous heating system just for your building?
Right. It's like the ultimate tension between collective reliance and rugged individualism, but, expressed through civil engineering.
Yeah, that's a great way to put it. And to analyze this for you today, we're looking at a highly specific practical engineering text. It's titled Practical Work Number 1, Technical and Economic Evaluation of the Efficiency of Autonomous and Central Heating.
Which is a bit of a mouthful.
It is, but this document outlines the exact mathematical methodology that professionals use to make these multi-million-dollar urban planning decisions.
Yeah, it's the real deal.
All right, let's unpack this. Our goal today is to look at the cold, hard math. We want to look at capital costs, operating expenses, and payback periods to see what actually makes sense. But before we get into the heavy math, we need to define the contenders stepping into the ring. Our source material lays out one baseline scenario and two distinct alternatives.
Right. So the baseline scenario, the standard against which everything else is judged here, is centralized heating from city heat networks.
The classic system.
Exactly. The legacy system for much of the developed world. Your building relies on heat generated miles away, usually at a massive municipal plant that produces both electricity and heat.
Right.
But to make this function, the city has to build and maintain miles of heavily insulated underground pipes. And then inside your building's basement, you have to install an individual heat point.
An ITP.
Right, an ITP. And that regulates the immense pressure and temperature of the incoming city, watered down to a level that's actually safe for your residential radiators.
And the text notes that a base case could technically be reconstructing an ancient neighborhood boiler. But for our deep dive today, that classic centralized city grid is the baseline.
Exactly.
And against that, we have alternative one, which is a roof boiler house. So this is autonomous heating, but it's scaled for the entire building. The building acts as its own mini city.
Yeah, you bypass the municipal heat network entirely. You just install a heavy-duty commercial boiler right on the roof of the residential tower, run high-capacity gas lines up to it, and boom, the building generates its own heat internally.
Right. And then we have alternative two, which just takes the decentralization all the way down to the studs. That's apartment level autonomous heating.
Yeah.
Every single unit in the building just fends for itself with its own wall-mounted heat source.
Total independence.
Exactly. And, to picture this hierarchy, I like to think about it like transportation. Centralized heating is like the city bus. It requires massive shared infrastructure. It runs on a rigid schedule dictated by the city, and you share the cost with everyone, whether you ride it every day or not.
That's a really good analogy.
Yeah.
And alternative one, the roof boiler, that functions more like an apartment building pooling their money to buy a shared neighborhood shuttle.
Right, exactly.
It's dedicated strictly to your building's residents. It operates on your schedule, but all the tenants still have to chip in collectively for the gas, the maintenance, the driver.
Yeah. And then alternative two, the apartment level boiler, is like owning your own personal car. You have total, absolute control. You can blast the heat in October if you want to.
But you're buying the engine, the fuel, the tires, and paying the mechanic all on your own.
Exactly. You're paying for all of it.
And these three specific options represent the macro, the mezzo, and the micro approaches to energy distribution. Tracking the math across these three tiers shows you exactly how the economic burden shifts as you decentralize the system. It moves from the state to the local community board right down to the individual homeowner.
Right. So we have our three contenders. We've got the bus, the shuttle, and the car. How do engineers actually crown a winner? Because, I mean, you can't just look at a monthly gas bill, shrug, and say one's cheaper.
No, definitely not. There's a massive hidden life cycle to these systems. And the text introduces the ultimate engineering equalizer for this, which is Formula 1.1. It calculates what they call reduced costs.
Or ZPR,
Right, CPR. And the reduced cost formula is really the bedrock of this kind of economic evaluation. It forces developers to look at the entire financial picture over time rather than just the immediate sticker shock.
So the formula dictates that reduced costs equals operating expenses plus discounted capital expenses. Let's break that down for everyone. Capital expenses, that's the upfront hit.
Yes.
It's the massive check you write on day one to buy the equipment, dig the trenches, weld the pipes. And operating expenses, that's the annual bleed.
The cost of buying the fuel and maintaining the equipment year after year.
Right. But the trick in this formula is how they handle the capital. They multiply it by a discount coefficient, a little lowercase e, and the source text specifically mandates this coefficient is locked in at 0.08.
Based on the industrial construction instructions, yeah.
But wait, isn't a fixed 0.08 discount rate kind of arbitrary? I mean, real-world inflation, bank interest rates, global energy prices, they fluctuate wildly. Why use a flat mandated number to decide a building's fate?
Well, what's fascinating here is that if you let every developer or local politician use their own custom projected discount rate, they're going to manipulate the math to justify whichever system benefits them most in the short term.
Oh, so they just cook the books.
Exactly. Yeah. The 0.08 coefficient acts as a forced standardized anchor. Think of it through the concept of the time value of money. Let's say a centralized heating system requires like $1 million more in upfront capital than a simple roof boiler.
Oh.
If you didn't spend that $1 million on basement regulators and underground trenches, you could theoretically leave it in an index fund earning, say, an 8% return annually.
Oh, wow. Right.
So that 8% lost opportunity, the money you aren't making because you buried your cash in infrastructure, has to be mathematically accounted for as a continuous cost of choosing the more expensive system.
Ah, I see. It forces an apples-to-apples comparison by balancing the heavy weight of immediate construction against decades of slowly burning fuel.
Exactly. So now we have to look at what actually goes into those buckets, what makes up the capital and operating costs for our three contenders. The text drills down into the specific physical components, calculating everything per square meter of the building.
Right, which keeps the scale perfectly fair, whether it's a small complex or a massive skyscraper. So for the central heating baseline, your capital investment involves digging up the street to lay the network pipes connecting your building to the municipal grid, plus the cost of that complex ITP down in the basement.
And that ITP is not a cheap piece of hardware. It requires high-end heat exchangers, commercial-grade pumps, automated sensors, all to take superheated, highly pressurized city water and safely transfer that thermal energy to the building's internal loop.
Wow. Okay, and for alternative one, the roof boiler, the capital skips the street trenches entirely, right?
Right. Instead, you're paying for a massive industrial boiler hoisted onto the roof, plus the heavy-duty reinforced gas supply lines running all the way up the side of the building.
And then for alternative two, the apartment model, the capital is just dozens of individual smaller boilers for every single unit, plus that maze-like network of gas pipes running through all the internal walls of the building to reach each kitchen.
Exactly. Now, if we look at the operating cost bucket for central heating, your operating expenses are dictated by the total annual heat consumption of the building multiplied by the specific tariff or the price of finished city heat.
Plus network maintenance, right?
Yes, network and ITP maintenance. But for the autonomous options, you aren't buying finished heat anymore. You're buying the raw ingredient.
Right. So your operating costs rely heavily on the total volume of raw gas you pump into the building, multiplied by the market price of gas, plus the maintenance for your boilers. It's exactly like the classic printer and ink business model.
Oh, the initial hardware versus the consumable.
Right. Central heating has massive upfront printer costs, laying municipal pipe, the giant basement heat exchanger. But the real danger is the ink, the specific cost of that city heat.
Because the municipality holds a monopoly on the ink.
Exactly. If they double the price of city heat because their aging plan is inefficient, you have no choice but to pay it. But with the autonomous systems, you buy a slightly more expensive printer for your roof, but you get to buy raw, unrefined ink natural gas at bulk market rates.
That's a very effective way to visualize it. But, the text forces us to look closely at the hidden liabilities in that printer analogy.
Okay, what do you mean?
Autonomous systems shift the physical maintenance burden entirely onto the building owners. The engineering formulas specifically list variables for this EEC for the roof boiler maintenance and I for individual boiler maintenance.
Right.
When you buy city heat, you're paying a premium, but you're outsourcing the headaches. If a municipal pump fails at 2 a.m. in a blizzard, the city dispatches a crew to freeze in the street and fix it.
But if you have a roof boiler...
Right? If your primary pump cracks in January, the building's residents are suddenly scrambling to find and pay a private emergency technician out of pocket. People routinely ignore this massive liability shift when they just look at how cheap natural gas is.
You're taking on the total liability along with the total control. But, a formula is just abstract theory. Does this actually hold up when a real building is facing sub-zero winter temperatures?
Well, to prove the methodology, the engineers actually tested this on a concrete, real-world case study. A 5-story residential building located in the city of Rivne, Ukraine.
Okay, so the specifications for this risen experiment ground the math in reality. The building has a total area of 2,000 square meters, and the engineering target is to maintain an internal temperature of 20 degrees Celsius, which is about 68 degrees Fahrenheit, across all the apartments.
But the climate outside is the real antagonist here. Riven's average outside winter temperature hovers just above freezing at 0.1 degrees Celsius.
But engineers don't build for averages, do they?
No, they build for extremes. They have to design this system to survive a worst-case scenario. In this case, a brutal 5-day stretch where the temperature plummets to negative 21 degrees Celsius.
That is nearly 6 degrees below 0 Fahrenheit. And this isn't just a brief cold snap. The official heating season lasts 182 days. That's 24 hours a day. Half the year is spent actively fighting off the freezing cold.
Exactly. So the engineers calculate the physical demands. They figure out that just to fight off the winter and keep the building at 20 degrees Celsius, they need 200 kilowatts of heating power. But the residents also need hot water for showers, washing machines, and sinks. And that requires another 80 kilowatts of power.
So they run these demands through the calendar year to find the total energy needed in gigacalories.
Right. And for context, a gigacalorie is a massive unit of thermal energy. It's the amount of heat required to raise the temperature of 1 million kilograms of water by 1 degree Celsius.
Right. So the engineers do the math for the year. Total space heating for the freezing Ukrainian winter takes 365 gigacalories. But the hot water takes 522 gigacalories, bringing the total heat needed to 887 gigacalories. Now, here's where it gets really interesting.
Now I know what you're going to say.
How does heating shower water take 522 gigacalories, which is significantly more energy than keeping an entire 5-story building warm through a freezing 6-month winter, which only took 365? How does the physics of that work?
It seems completely backward, I know. Until you factor in the physical properties of water and human lifestyle habits, space heating is fighting a dramatic temperature difference, but it's fundamentally a seasonal sprint. It only runs for those 182 days.
Right.
And it's fighting an average outdoor temperature of 0.1 degrees Celsius, not the negative 21 degree extreme every day. Plus, once a well-insulated building is warm, it retains a significant amount of that thermal mass. You're basically just topping off the heat.
So once the walls are warm, you kind of coast a bit.
Yes. But hot water, that is a brutal, relentless marathon. It is a 365-day demand. Think about the physics. You're pulling fresh water from municipal underground pipes that might be sitting at a freezing 5 or 10 degrees Celsius.
Oh, wow.
You have to instantaneously heat that dense, heavy liquid up to 55 or 60 degrees Celsius for a scalding shower. And you don't retain any of that heat. It immediately washes down the drain.
Right. And the next person who turns on the tap requires the system to start all over again with freezing groundwater.
Exactly. This perfectly highlights how daily human habits, 30-minute showers in July, running the dishwasher twice a day, drive urban energy consumption just as much, if not more, than the local weather patterns.
That is genuinely staggering. We view the winter as the great energy enemy, but we're actually battling our own relentless demand for a hot shower in the middle of summer. So to produce this massive 887 gigacalorie demand autonomously, the source calculates the building will have to burn over 117,000 cubic meters of raw natural gas.
So we finally have all the variables to settle the debate. We have the physical demands, the climate data, and the fuel volume. Now the engineers run the Rivne building's actual numbers through Formula 1.1 to declare an economic winner between central heating and the roof boiler.
Okay, let's look at the results. The text uses Ukrainian hryvnia, but what really matters to you listening is the massive ratio between the two systems.
Mhm.
The central network requires an absolutely massive upfront capital investment.
Huge.
Per square meter, you're paying nearly double the upfront cost to connect to the city grid and install that basement regulator compared to just buying the roof boiler.
The capital difference is staggering, yeah. But the operating costs are where the central system truly punishes the building. Because you're forced to purchase finished, marked-up city heat from a municipal monopoly, the operating cost per square meter is astronomical.
Like, how bad is it?
The monthly operating costs for the central system are nearly 7 times higher than buying raw gas for a roof boiler.
7 times higher just to run it, man.
Yeah.
So we plug these ratios back into the magic reduced cost formula operating plus 0.08 times capital. The central system comes out to roughly the 13,265 hryvnia per square meter in reduced life cycle costs.
Right.
But the roof boiler, it comes out to a beautifully low reduced cost of just 489 hryvnia per square meter. It is a fraction of the cost over its lifespan.
And this brings the engineers to their final verdict. The text defines profit as the mathematical savings generated against the central pipeline. By subtracting the roof boiler's reduced cost from the central heating's cost, the roof boiler generates a massive profit of 876 hryvnia per square meter for the building.
I want to clarify this concept of profit for you, the listener, because the engineering terminology can be a bit misleading here. This profit is not a physical check that the gas company hands you at the end of the year. Nobody's getting rich off this.
Right, it's captured savings.
Exactly. It's money not burned in the furnace. It's exactly like finally cutting a massive $200 a month cable television subscription and switching to a $15 streaming service. You don't magically get a raise at work, but your bank account completely stops bleeding every month.
And if we connect this to the bigger picture, that captured savings is the critical metric. The engineering text introduces Formula 1.2 here, which is the payback period.
Okay.
Developers take that massive pool of captured savings, that profit per square meter, and use it to calculate exactly how many years it will take for the roof boiler to literally pay for its own initial installation. Because the operating costs of raw gas are so incredibly low compared to city heat, the roof boiler pays off its upfront capital in record time.
The math in the text is undeniable. In this specific economic scenario, the autonomous roof boiler absolutely crushes the central heating system. The neighborhood shuttle destroys the city bus.
It really is.
So what does this actually mean for you? Whether you're renting an apartment, buying a new house, or sitting on your local HOA board, the way your building generates heat dictates a massive, often completely invisible portion of your daily living expenses.
Understanding the relationship between the upfront capital, the printer, and the long-term operating costs, the ink, makes you an empowered consumer. You stop looking just at the superficial monthly bill, and you start looking at the hidden life cycle of the infrastructure you're buying into. It changes how you evaluate real estate and urban living.
It does, but, the undeniable victory of the roof boiler raises an incredibly provocative final thought. We just proved mathematically that autonomous heating is vastly superior in terms of cost and efficiency for the individual building. The smart money, the rational economic decision, is to cut the cord and disconnect from the city. But what happens to the larger city infrastructure when all the profitable, efficient, well-managed buildings realize this and actually do disconnect from the central grid?
Well, you trigger what economists and urban planners call a utility death spiral.
A death spiral.
Yeah. The massive municipal heating plant still has enormous fixed costs. It still has to burn fuel. It still has to employ technicians. It still has to maintain miles of degrading underground pipes.
Right, and if the wealthy, organized buildings leave the grid to save money with roof boilers, the city loses its best-paying customers. So to cover those massive fixed costs, the city has no choice but to raise the price of city heat for everyone who's left on the grid.
Which makes the ink even more expensive, causing even more buildings to realize the math makes sense to leave.
It creates a feedback loop. Until eventually, you're left with only the poorest, oldest, most underfunded buildings, the ones that literally cannot afford the upfront capital to buy their own roof boilers, carrying the entire financial burden of an aging, oversized, inefficient central grid.
It's a really harsh reality.
It is. Is the cold, hard math of individual efficiency accidentally creating a citywide crisis? By rationally optimizing our own little vertical monuments to save a few dollars, are we inadvertently destroying those hidden underground veins that once kept the entire city alive? It's definitely something for you to think about the next time you hear the radiator hiss and turn up the thermostat.